in the traditional sense of Lagrange multipliers. It doesn't make sense to me. Let's just say it like that. Okay, so this last one I wanted to do was I wanted to do a centroid problem. So I wanted to find x bar and y bar. Okay, and I want to find that of the shape So I have this shape that's a polar equation for the shape, and I want to figure out the centroid of the shape, so the geographical center of mass of this shape right here. Okay, so what is this shape? Does anybody know? Everybody took pre-calc. Somebody should know, right? Me neither. Okay, so let's think about what's going on. We'll plot some points and it'll make some sense, okay? So when theta equals 0, that's when the angle between the x-axis and the radius is 0, so that's along the x-axis. R equals 10 plus cosine of 0. So what's cosine of 0? 1, so R equals 10 plus 1. So when theta is equal to 0, R is equal to 11. So we have a point out here, 11. Okay. When theta is equal to pi over 2, or 90 degrees, what is R equal to? 10. Okay, good. So far so good. Rocking out. And when theta is equal to pi, so we got the angle between the x-axis and the radius is pi, or 180 degrees. We're going along the negative x-axis. What is R? Right, well it's 10 plus cosine of pi, so it's 10 minus 1 is 9. And then again, when we're down here at 3 pi over 2, we get this 10 again. So it's almost a circle, but not really. There you go, I made it look even less like a circle than it actually looks like. But it's not a circle. Okay? So, you're welcome. If you looked at it on a computer, if you Wolfram Alpha this, you might think it was a circle. Because it's close to a circle, but it's not a circle. Because the center is still here, but there's a longer radius this way than there is this way. Theta is still spinning around this point, but it's thrown off, so it's not a real circle. It looks like that. Okay. So we're trying to find the centroid of this thing. Alright, so what do we do? I forgot. What do we do to find the centroid of this thing? Find the centroid of this thing. Well, we got to figure out what R goes to and from, and that's pretty easy. R is going from this function that mapped us out this egg is where it ends up at, but we got to hit all the points in the middle. We got to start at 0, so R can go from 0, but it can't go past this egg. Call it an egg. And where does theta go from? Well, theta did its complete revolution because it spun all the way around the origin. So theta went all the way around the origin. So in polar coordinates, this double integral for the area, because a second ago I said volume, but I had a triple integral, so remember double integral is area. So the equation for x bar in 2 dimension is going to be the area times x dx dy, right? This is over the shape, what do they call it? gamma and omega. So the shape omega. This is our egg was omega. So with the smooth switch to polar, we could say that x bar, well, let's just find the area first. We got to find the area first. So our area is going to be equal to, well, theta is going from 0 to 2 pi. R is going from 0 to 10 plus cosine theta. And we got r dr d theta. Not that bad, right? Even though this is the polar shape and everybody says, I don't remember anything about polar shapes, or I don't remember what this function actually looks like, and how do I know if it's going to be a petal leaf or a four-leaf clover or whatever. Just plot some points out, plug it in your calculator, do whatever it takes. It's not that bad. Okay? And then, of course, from here we can go x bar is equal to 0 to 2 pi, 0 to 10 plus cosine theta, and we have here x is supposed to go in here, but we changed coordinates, so we have to go r cosine theta. Don't forget our Jacobian, r squared. I'm in the corner, you guys can't see anything. I'll write it again over here. Well, I forgot to divide by, for those that can see this, divide by the area. Okay. So over here, we have x bar equal to 0 to 2 pi, 0 to 10 plus cosine theta, r cosine theta, because that's what x equals. Don't forget the Jacobian, you have to say r squared, dr d theta, all divided by the area, which we defined over there. You could, again, this answer has two double integrals in it. So you have to, we don't ask you to evaluate it, we just ask you to write it. Okay? So if you see a polar equation on the test tomorrow, don't wet your pants. Just remember, it's just a different coordinate system. Okay? Theta's going to keep spinning around theta's going to keep spinning. All right? The world's not going to end. Theta's going to keep spinning, and r is going to be the distance from the origin. Okay? All right, we good? All right, this one was pretty easy. Y bar would be the exact same thing, but r squared sine theta. Because the equation for y bar is a equal y dx dy. So when you change your polar coordinates, you remember that y is r sine theta, and then it looks exactly like here, but instead of r squared cosine theta, you have r squared sine theta. Yes, the point, the integrals will evaluate to a number, right? Yeah, so the point would be like integral, integral over, integral, integral, comma, integral, integral over, integral, integral. Okay, so this would be, an ordered pair. Or you could just define it like this, x bar, y bar. And that thing's not symmetric in x, so it's not just going to be 0. A lot of times you see things like that, and you think, oh, centroids, it's symmetric. If it's symmetric in something, then you know it automatically is going to be 0. But that's not symmetric in x, even though it kind of looks like it. If I were to truly exaggerate it, it would look like, and go a long way this way, and then come back up with the axis right here. That's a true exaggeration of it. So you can see it's symmetric this way, so the centroid in y is going to be 0. But really, x is going to be offset somewhere over here. X bar. Okay. So this is an exaggeration. If you look at it, it looks like a circle.